Okay, good afternoon. Uh, let us discuss about the momentum equation for multiphase flow. We are discussing about the governing equations, and in particular continuity equation we have discussed in the previous lecture. So, let us now discuss about the momentum equation. So, first can you tell me from your understanding of single phase flow, so momentum equation is a scalar equation or vector equation? Scalar or vector? If I am writing complete momentum equation. See, whenever I write complete momentum equation in tensor notation, then or in vector form, then it's a single equation, and if I do substitute each quantity, okay, so for single phase flow, if I write momentum equation, what it is? Tell me the terms. Del rho v vector by del t plus rho v vector is equal to minus gradient of p plus divergence of, or if I assume Newtonian fluid of constant viscosity, then mu times Laplacian of v vector plus rho into g vector. Okay, now if you over here try to replace the individual term, what will be v? U I cap plus V j cap plus W k cap. Okay, del will be del by del x, I cap plus del by del y, j cap plus del by del z k cap. Okay, now if you see in first term, what you will be getting? Del rho u by del t I cap plus del rho v by del t j cap plus del by del t rho w into k cap. Okay, so likewise if you replace the all the vector quantities in all the terms, then ultimately what you are getting? You are getting your terms with I cap, j cap and k cap. So it means momentum equation is nothing but a vector equation, because momentum is a vector quantity. Okay, now from this momentum equation, if you segregate all the terms involving I cap, all the terms involving j cap and all the terms involving k cap, then you get nothing but your x momentum equation, y momentum and z momentum equations. Is this point clear? So before starting the discussion of momentum equation for multiphase flow, this should be clear to you. Another important point you have to understand is that in this equation, this particular term, which should be divergence of, not vector, stress tensor tau ij. Okay, so which should be divergence of stress tensor, this tau I have replaced with mu times rate of strain in terms of gradients of velocity. Okay, so this type of formulation is applicable only if I assume the assumption of Newtonian fluid having constant viscosity. Okay, so that is the reason when I do this substitution, this equation is only applicable for Newtonian fluid. All are clear with this idea? Now with this basic understanding, let's try to, okay, before this, can you tell me how I can write this equation in the tensor notations? Del rho ui by del t plus divergence of or del by del x k rho ui into uk, okay, minus del p by del x I, or let me write say k. I am writing momentum equation in kth direction. Del x k Is this one clear? Plus mu times del square by del xi del xk times what? uk. Okay, and what else I will be getting? Plus rho into gk. Okay, so now what is this equation? This equation is actually kth direction momentum equation. Okay, all are clear with this idea? So this is kth direction momentum equation, and my k will be varying from 1 to 3 in order to write three principal directions. Okay, so now you come to this equation. What we have in this equation? What is left hand side? F, capital F force, N represents force acting on nth phase, K represents in kth direction, and capital T in the subscript represents the total. Okay, so F and K is total force on nth phase in kth direction. That is the physical interpretation of this single term. Is this point clear? Now we know from Newton's law of motions what is momentum equation, nothing but Newton's law of motion. Okay, so we know from Newton's law of motion that force has to be equal to mass into acceleration. Okay, and for fluid medium we have two types of acceleration, one is local acceleration and other is convective acceleration. So local acceleration is del by del t rho n into un k. Okay, because we are writing momentum equation in kth direction, so that's why acceleration has also to be accounted for in which direction? Kth direction only. Okay, so rho n into un k, and then because in the control volume n phase is not present in entire volume, it is only present in alpha n fraction of the control volume, so that's why rho n alpha n into u. All are clear with this first term? Anyone is having any doubt? Then we have second term. So second term has to be, it has to account for momentum coming from all the directions in the particular kth side. So del by del xi with rho n, uni, unk and alpha n in multiplication. Is this one clear? Anyone is having any doubt? So see, these terms are common to that of our single phase momentum equation. The only addition we are doing over here is we are writing n, means we are talking about a particular nth phase. And second important thing is because nth phase is not present in complete control volume, it is only present in alpha n fraction. So that's why alpha n I am multiplying over here. So now you can have direct correlation of this equation with the one which we have written for single phase flow. The only difference is the force which we are writing over here, that at the moment I am writing total force and I have not divided it into its individual constituents. Okay, so can you tell me in single phase flow when we divide this force what type of forces we have? So first categorization is for single phase flow we have body force and other is surface force. Okay, and surface force, if you recall, we further categorize into,
sir, in this you have written del xi, whereas where you are writing there you have written del xk.
here. Okay, so yes, this is the mistake, it should be I only, because why this will be I? Because whenever we will be writing mass flow rate coming from all the directions we have to account, but its velocity has to be only in which direction? Kth direction. Is this one clear? See, whenever we take a control volume, how we get this equation? This is my control volume, x, y, z. From here I will be having mass flow rate as, mass flow rate per unit area is rho u, and velocity is also u. So momentum will be becoming rho u u. Okay. Here it will be rho u u plus del by del x of rho u u into dx. Is this point clear? Then when I will be writing mass through this side, so mass through this side will be rho into v. Okay, but momentum I have to write only in which direction? X direction. So this will be rho v into x direction velocity at this point. So rho v into u. Okay, and here also it will be rho v u plus del by del y of, is this point clear? Into dy. Now you can see when I will be taking this momentum minus this momentum, then from this I will be getting del by del x of rho uu plus from this momentum in y direction, I like mass flow rate in y direction but momentum in x direction. I will be getting del by del y of rho v into u. So now you can understand that x is varying with I, okay, and equivalent velocity is also varying in I. Is this one clear? All are clear with this idea? So whatever the mistake I have done here, you can correct this. It will be del xi into vk, and point is clear. So let's go here. So one will be body force and other will be surface force. In surface force, we further do two categorization. One surface force which is acting at the boundary, that will be because of the pressure, and other surface force will be because of surface tension, because single phase flow right now I am talking about. So other surface force will be because of the which type of stresses? Deviatoric stress. Okay. What do you mean by deviatoric stress? Please tell me. All of you have studied fluid mechanics. So what do you mean by deviatoric stress? Sigma is the total stress tensor. Sigma is the total stress tensor. We write sigma is equal to minus P into delta Ij plus some stress component tau, and that tau is called as actually deviatoric stress tensor. Is this point clear? And this deviatoric stress tensor only comes into play when we have fluid in motion. So it means this comes because of the viscous component of the fluid. So this comes because of the viscosity of the fluid. Is this point clear? All are clear with this idea? So it means that if I talk about single phase flow, I will be having body force and surface force. Surface force further will be having two types, pressure force and deviatoric stress. Only this much is our understanding for a control volume which is there in the single phase flow. But what will happen for a control volume which is involving the multi-phase flow? So in multi-phase flow, what will happen? This control volume, say I am making the 2D representative, this control volume will not be having only single phase, but it will be having large number of small other phases also present. Is this point clear? Now, one important point is, all the forces which are coming for single phase flow, these will be there. But in addition to that, whenever I will be writing a particular equation, say this is my nth phase. When I will be writing a equation for nth phase, then on this nth phase there will be some forces from the surrounding continuous fluid. Is this point clear? All are getting this idea or not? Okay, so typically what happens, say if you have a liquid flowing, and in this flowing liquid if you drop the particle, what will happen? Because of the flow of the liquid, this particle will experience some force, so that force also you have to account for. Is this not clear? So whenever fluid flows, and in that fluid flow if you have put some particle, that particle will be experiencing some force because of the surrounding fluid medium. Okay, so that force is called as interaction force on nth phase due to surrounding phases. Is this point clear? So in a single phase situation, only two types of surface forces were coming into picture, which were pressure force and the viscous force. And for a single phase flow, because entire control volume is filled with the same type of fluid, these viscous stresses and pressure forces were only acting at the boundaries of control volume. Okay, so these forces were only acting at the boundaries of the control volume, because within it the shear stress and pressure were balanced. Okay, but for multi-phase flow, because within the control volume there will be particles present, a particular phase will be present in the surrounding of other phases, so there will be some interaction force on nth phase due to the presence of surrounding phases in the control volume. Is this point clear? So the previous forces which I discussed on the slide, all these forces are acting only at the boundary of the control volume. Is this point clear? But one force which is the interaction force, that is acting on particles within the control volume, so it means it is acting on boundary of the particles. Is this point clear? So previous surface forces, pressure and this, these were on the boundaries of the control volume, and this interaction force acts at the boundary between the nth phase and the surrounding phases. All are clear with this idea, or anyone is having any doubt? Now let's individually try to calculate all the forces. So first force is body force. How much will be the magnitude of body force? We know for single phase flow, body force per unit volume is equal to rho g vector. Okay. Over here, along with the rho g vector, we have to also account for the volume fraction. So that's why body forces acting on nth phase has to be alpha n rho n into g. All are clear with this idea? Then, this is which force? Tell me. Surface force. Which type of surface force? This type of surface force which is acting on boundaries of control volume. Where this force is acting? It is only acting at the boundaries of the control volume. Okay. So, to understand this force, whatever the formula I have written over here, we have to make one assumption. Okay, what is that assumption? Let me tell you. As I told you, in multi-phase flow system, I will be having multiple particles present, and some of the particles may lie on the boundary of the control volume. Is this point clear? If I have to calculate this surface force by considering that some particles are partially crossing the boundary of the control volume, then what I have to do? I have to individually determine that how much fraction of boundary is cut by which particular type of phase. Then only I can calculate the corresponding forces at the surface. But this type of analysis will be becoming extremely complicated, because at each and every moment we will not be able to estimate the proper distribution of the particles crossing the boundary of the control volume. Okay, so here we will be making one assumption. What assumption we will make? We will assume that wherever particle is present, there I have deformed my control volume in such a way so that everywhere only, so here you can see these are the portions where I have deformed the boundary of control volume, and this boundary of control volume I have deformed in such a way so that always continuous phase is in contact with the boundary. Is this point clear? What assumption I have made? Please tell me. So, wherever my particles were crossing the boundary of the control volume, there I have deformed the boundary of the control volume in such a way so that my new control volume is of this deformed shape. Okay, and everywhere we consider that particles, all the particles are well within the deformed boundary of the control volume, and boundary of control volume is everywhere having contact only with the continuous phase. All are clear with this idea? When we are making this assumption, our surface area of control volume is slightly increasing. Okay, so surface area of the control volume is slightly increasing, but this increase in surface area is negligible in comparison to the original surface area of the control volume, because we have chosen the size of control volume in such a way so that we can have finite number of particles within the control volume. Okay, so individual particle size will be very small in comparison to overall size of the control volume. That's why the deformed area will be very less. Is this point clear? So because of this reason, the assumption of deformed boundary does not make any major change on the size of the control volume. All are clear with this point? This is very important line. Okay. Now, because we have made assumption that only continuous phase is there in contact with the boundary, so whenever I will be calculating the surface forces which are acting at the boundary, their stress tensor, the total stress tensor of continuous phase will only come into picture. Is this point clear? Are you getting this point or not? Okay, because boundary is only controlled by the continuous phase, so that's why stress tensor of continuous phase. So it means though I am writing nth phase equation, but when I am writing the surface force acting at the boundary of control volume, in that I am clearly writing that stress tensor is only acting for sigma c. I am not writing sigma n. Okay, because stress tensor at the boundary of control volume is only applicable for continuous phase, which is making contact with the boundary. So this is sigma c ki, because it's a tensor quantity, so it will be having direction as well as the plane. So it is having two indices I and k. Okay, and this del by del x k is my representative. All are clear with this idea? So it is the total stress tensor. Total stress tensor means it is including pressure term also and deviatoric stress also. All are clear with this idea? So this total stress tensor sigma c ki will be equal to minus p into delta ki, which is the pressure term, and plus sigma c ki, and in the subscript I am using d in order to represent the deviatoric part, and this deviatoric part is only coming into picture because of the viscous effect. So Now, if I do substitutions of F and K T, so what I will be getting? My this is remaining as it is for nth phase, we don't have any change. But in right hand side, first term is representing which force? Body force. Second term is representing, if I do the substitution of this P delta Ki into delta C Ki in this stress tensor term, then I will be getting del P by del xk minus del sigma C Ki d divided by del xi. Okay, so this force is surface force at boundary of control volume. All are clear with this point? Now, one important point, because I am writing this equation for which phase? Nth phase. It is not always true that nth phase is my continuous phase. Nth phase can be dispersed phase. So, but this surface force will only be, surface force at the boundary of the control volume will only be acting for which? Continuous phase. So that's why along with this term I have used one delta n over here. Okay, so this is my Kronecker delta operator. What is the need for using this variable? The need for using this variable is delta n will be equal to 1 for n is equal to c, and delta n will be equal to 0 for n is not equal to c. Like if any other phase I am using, it means that other phase is nothing but my dispersed phase which is not making contact with boundary of control volume. So for that particular, this term has to be equal to 0. Okay, and this term will be only coming into picture when my nth phase is nothing but the continuous phase. All are clear with this point or not? Clear? So this is the surface force, but this Kronecker delta operator is ensuring that this force will be coming into picture only when n is equal to c, and if n is any other phase, then this force will not come into picture, because that particular phase is not making contact with the boundary of the control volume. Okay, but one more additional force I have written over here, F and K. What is this F and K?
Force is acting on a particle due to surrounding phase.
Yes, so this is the interaction force on nth phase due to surrounding phases. Is this one clear? And this particular force is something which will be simply equal to 0 for a single phase flow, because in case of single phase flow we don't have any surrounding phases present. Okay, but for multi-phase flow this interaction term has to come into picture. So at the moment we are not defining it how to calculate interaction force, but we are just writing it. Okay, is this one clear? So this equation is nothing but my individual phase momentum equation. So this complete equation is called as individual phase momentum equation. All are clear with this idea?
लास्ट वाली टर्म में डेल्टा की आई कितनी है पी के साथ
Here,
अंदर
here,
डेल्टा पी ओ डेल पी
del P. Okay. Now you tell me, what is pressure? A tensor quantity or a scalar quantity? In fundamental way, if you see, pressure is again a tensor quantity because it requires a surface and it is having direction. But one special nature of the pressure is that it always having uniform value around the fluid particle in all the directions, and it's having unique direction that it always acts in a direction normal to the boundary. So these two features makes pressure a scalar quantity. So that is the reason there is no subscript with the pressure. Okay, so in all the directions, whether you will be calculating pressure on control volume in x direction, y direction, z direction, everywhere it will be having the same magnitude. Okay, is this one clear? Now, okay, again I think repeat of same slide. Yeah. So up to this point it is clear. This is individual phase momentum equation. Now comes the important term. What does it is representing? Summation of n of all interaction forces is equal to 0. What it means?
सर काफी सारे पार्टिकल तो रैंडम डायरेक्शन में लग रहा हो तो नेट 0.
No. So it means that if you have say two phase system, okay, so if you have water flowing and air flowing together, and let us assume air is moving faster in comparison to water, what will happen at the interface? At the interface, air will try to pull the water molecules. So if you see force acting on water boundary, it will be towards this side, so force on water due to air. Okay, but if you see, if water is moving slow, then water will try to slow down the air by the same amount of force but in opposite direction. So it means that on air, if I calculate the force, it will be FAW but with opposite direction, and from here we will be finding that FWA is equal to minus of FAW. Is this point clear? Now if you combinedly write all the things together, then this interaction term of air and interaction term of water will be added together and it will give you the 0.
Sir, but we are talking about one phase only, right? Because summation over n phase.
Summation over n, what it means? All the n phases we are considering. Okay, so summation over n means FAK plus FBK plus FCK, etc. So K means force in kth direction, but ABC means force on phase A because any of the surrounding phases. Is this one clear? Now only you will not be having this situation. In a multi-phase scenario, you can have that this is some particle, part of this particle is say covered with water and part of the particle is covered with air. Then what will happen? On this particle, say this is solid particle, so FSW will be having some x magnitude and FSA will be having say some y magnitude. But when you will be calculating force on air, then force on air because of particle will be equal to minus y and force on water because of particle will be equal to minus x. And when you will be doing complete summation, then ultimately it will be becoming 0. Okay, this point is clear. So sum of the interaction forces, only the interaction forces on all the phases, if I do it sum, that has to be equal to 0. Now comes one important point. If I assume that I only have two phases present in the system, okay, I only have two phases. One is continuous and other is dispersed phase. Okay, so in this scenario, what will be happening? The force acting on dispersed particle in kth direction, interaction force, that will be equal to minus force acting on continuous phase in kth direction. Is this point clear? And this has to be equal to, now it is important to understand, interaction force can be of how many types? Please tell me. You have a particle. On particle, surrounding fluid can apply forces in how many ways? Do you have some idea about the drag force acting on solid uh, objects placed in the flow field? First thing is it will be only acting at the surface. Other thing, it can be divided into two ways. All of you, please revise your basics of fluid mechanics. Have you studied flow of fluid over aerofoil? Have you studied? All of you have studied. So when I say that drag force acting on aerofoil, it first point is very clear. You have correctly mentioned that all the forces which are acting on this aerofoil structure because of the flow, these will be acting along this particular boundary. Okay, so forces will be of surface nature. Okay, but the forces can act on this aerofoil in two ways. One can be across this aerofoil, there will be some pressure profile. Okay, pressure at each and every point of the aerofoil will be different. Is this one clear? Say this is the pressure profile across the boundary of the aerofoil. So because of this pressure difference in the direction of the flow, so some pressure is acting over here, some pressure is acting from the back side. Because of this pressure difference in the direction of the flow, whatever force is acting, that is called as FDP, which is called as form drag or pressure drag. What else we have? Other than this, we have some shear stress which will be acting over this because of the viscosity of the fluid medium. Okay, so because of the viscosity of the fluid medium, whatever force acts on this surface in the direction of the flow, that is called as skin friction drag. Is this one clear? So over here, the total drag force which is acting on an object placed in the surrounding fluid is acting on the particle in how many ways? Two ways. Okay. One is in the form of, so this is, I have only talked about the drag force, but if you consider, so drag force is in the direction of the flow. If you consider force in the direction normal to the flow, then we will be having lift forces. Okay. So of course we have to account for all the type of forces, and there also we will be finding that force either will be because of the pressure distribution and because of the skin friction. Okay, mostly the aerofoil shape is such that magnitude of lift force because of pressure distribution is actually significantly high in comparison to magnitude of lift because of the skin friction. So that's why for lift force majorly the pressure distribution is responsible for generation of lift force. However, when we do calculate the drag force, then pressure and skin friction both have almost relative magnitude, comparable magnitude. So that's why both are to be accounted for. Is this point clear? So overall point is that because the total stress tensor which will be acting on this boundary, it will be having two components. One component will be because of the pressure and other component will be because of the viscous stresses which are acting on this boundary. Is this point clear? So the contribution which is coming because of the pressure, particularly for drag force, that is called as form drag or pressure drag, and contribution which is coming because of the viscous stresses, that is called as skin friction drag. Is this one clear? Now, instead of this aerofoil, if I take a spherical particle present in the flow field, on this spherical particle also I will be having some pressure distribution. Say I will be having some pressure profile, something like this, that on its leading edge pressures are high and in the trailing edge pressures are low. So there will be some force on this particle because of the variation of the pressure. Other than that, on this particle I will be having gradient of velocity also. Here no slip condition, and away from this particle velocity will keep on increasing. So there will be some contribution of shear stress also. Is this point clear? So now here what we will be finding? We will be finding that the forces are coming because of the pressure and the dielectric stress. Okay, interaction forces. So that is what I have done. Now here you can see the first part represent the interaction force because of the pressure distribution, and as we are calculating this force because of the on the dispersed particle, so I am multiplying with this volume fraction of dispersed particle. All are clear with this point? And force acting because of the pressure on a control volume, we know from our basic understanding of fluid mechanics that force because of pressure per unit control volume is equal to minus gradient of P, and gradient of P in tensor notation can be written in terms of del by del xk into. All are clear with this idea? And then I will be having some second component f dash dk, and this component is because of the deviatoric stresses. Okay, so for estimating this component I should know the complete shear stress profile, then only I can estimate this particular component. All are clear with this point? So interaction force, then I have divided into two components. Okay, now what we have done one simple simplification. In the previous equation, if I use these two terms together and then if I apply the principle of separation of variables, okay, on these are nothing but the differentiation. So on this differentiation, if I apply chain rule, then ultimately what I will be getting rho n alpha n as common into del u nk by del t plus u ni into del u nk by del xi, plus I will be getting one more term plus u nk as common into del rho alpha n by del t plus divergence of rho alpha n into, okay, what is this? Individual phase continuity equation. And for single phase continuity equation this term is equal to 0, but for this type of continuity equation, individual phase continuity equation, this term will be equal to in. Okay, so now what I have done over here, already I have considered this factor in the right hand side, so I am actually removing it from here. Okay, so this factor I have taken to right hand side, which is minus in into u1k. All are clear with this idea? How this in and unk has come? Okay, now this is as it is. This is as it is, which will be only acting for continuous phase, and f and k is the interaction term. Now what does it is representing? The first term is local derivative and second term is u dot into del u. So this is advective acceleration. Okay. So what is del u by del t plus u dot del u can be written as d by dt of total derivative. Okay, so now okay, I have not written, so I can write this term as rho n alpha n into dn by dt of unk. Okay, so this will be my left hand side, and this will be equal to body force plus interaction force minus in unk minus delta n of this. Now what does this dn by dt of unk representing? It is nothing but Lagrangian derivative of the velocity field, okay, which is representing total change in momentum for control volume. Okay, now for multi-phase flow you will be finding that one more term is coming into picture which is also causing some momentum change, and that momentum change is because of the mass interaction term within the control volume. So in into unk represents momentum change within control volume due to mass interaction term. Is this point clear? So say if you have liquid mass, it is getting converted into vapor. So once it is getting converted into vapor, its molecules will be having different motions. So overall momentum of the control volume will change. If you have a vapor mass which you are having molecules rapidly moving together, once these are getting converted because of the phase change process into the liquid, then these molecules will come close to each other and they will be having more stronger cohesive forces. Okay, so their overall momentum will decrease. So that is the reason that if within the control volume some phase change is happening, if it is going to vapor, then molecules are becoming far apart and having more random motions. But if it is changing from vapor to liquid, molecules are coming close to each other and their random motions are suppressed, their mobility is decreased. So because of this process, whatever change in momentum will be happening, that change in momentum is accounted for in this particular term. All are clear with this idea? So this is now my complete picture of the momentum equation for nth phase. Now what I have done, what is this? Now after looking into the equation, can you tell me what is this? I have written momentum equations for individual phases and then I have taken the sum. Okay. So left hand side is very simple, direct summation I can do. But in the right hand side, what I have got? In the right hand side, what I will be getting? In terms of body force, I will be getting rho A alpha A into GK plus rho B alpha B into GK. Likewise, so rho 1 GK will be coming common, rho A alpha A plus rho B alpha B, what it will be giving me? Mixture density. So this rho is actually mixture density. Now when I am doing sum of all the interaction terms, what it will be equal to? 0. So interaction term I have not written over here. Okay. When I will be doing sum of all the phases and consider forces acting at the boundary. So at the boundary, forces will only act for a single continuous phase. So that's why surface forces are only written for the continuous phase, including deviated stress tensor of continuous phase. Okay. So this is my combined phase momentum equation. This part is clear. So this is nothing but my combined phase momentum equation. Okay, now let's try to analyze one situation. Do we have time? Yes. Let's consider that I have some fluid as continuous phase, and in this fluid solid particles are sedimenting at uniform velocity. So situation is you have a surrounding continuous fluid and in this solid particles are actually sedimenting at the what? Uniform velocity. So this is uniform velocity sedimentation of particles. For this situation, can you write down the momentum and continuity equation for dispersed phase and continuous phase? Please write down. Let's write down only the momentum equation. So you tell me, what will be momentum equation for dispersed phase? In the momentum equation on left hand side, how many terms we have? Local acceleration plus convective acceleration. Particles are uniformly sedimenting with uniform velocity. It means velocity is neither changing with space nor changing with time. So total acceleration term in the left hand side will be equal to 0. So for dispersed phase, if I write momentum equation, then left hand side is 0. In the right hand side, will I be having, so what force I will be having? Body force. Body force will be rho d, density of dispersed phase particles, alpha d, volume fraction into g, and gravity is acting in downward direction, so minus sign will be coming in the body force. Okay, what else? Interaction term. So let's consider Fd. K is the interaction force which is acting on dispersed particle because of the surrounding phase. All are clear with this idea? Then will I be having surface force at the boundary of control volume? Because dispersed phase is not lying at the boundary of the control volume, so surface force for dispersed phase and boundary will be 0. So this is my momentum equation for dispersed phase for this simplified situation. What will be momentum equation for continuous phase? Please tell me. Continuous phase is stagnant. What will be its acceleration? 0. But continuous phase is crossing the boundaries of the control volume. So it will be having pressure force minus del P by del X. Let me consider this direction is X. If you have to consider Y, then it will be Y. Okay. So it will be only in single direction because we are trying to write momentum equation only in the direction where particles are falling. Okay. And what else? Deviatoric stress tensor. Del by del X of sigma C Ki plus what else? So this is all surface forces. Then body force. What will be body force? Rho C alpha C into G. And what else? Interaction force on continuous phase in kth direction. If this continuous phase is applying some force on particles, then particles are also displacing it from the beneath them. So it means particles are also applying some force on the continuous phase. That is FCK. Okay. But oh sorry, this will be negative. Yeah. Now what I will be getting? Because only two phases are present, so FDK will be equal to minus FCK. Is this one clear? And from here, what is FDK? FDK is rho d alpha d into G. So from here FCK will become minus rho d alpha d into G. I can replace this here. If my fluid is stagnant, okay, fluid is stagnant, will it be having any deviatoric stress? Deviatoric stress only comes when there is shear strain, fluid motion. So deviatoric stress will be 0. All are understanding this point? So it means that minus del P by del X will become simply equal to rho C alpha Cg plus rho D alpha D into G. G is coming common, minus del P by del X has become rho C alpha C plus rho D alpha D. What it is? Rho into G. What it means? Mixture density, whatever weight of the mixture is there, that weight of the mixture is balanced by the corresponding hydrostatic pressure gradient in X direction. Is this point clear? So, weight of the fluid mixture is simply balanced by the hydrostatic pressure gradient present in the system. Is this point clear? So you can see now, sometimes the situation may look very complex to you, but whenever we are imposing assumptions, though this particular expression is loaded with so many assumptions, uniform flow, uniform velocity, surrounding stagnant fluid. So in practical scenario, getting all these assumptions will be, in practical sense, will be very difficult. Okay, so we will not be able to neglect many of the terms which we have neglected now. So upon neglecting, the solution has become easy, but once we consider all the terms, then solution will be complicated. Is this one clear? So this, for this situation, these are the equations written and this is the final expression. So already I have derived it. Okay, now let's stop and we'll discuss further in the next class.